Hello everyone, my name is Jessic Moreno and today I will present the paper with title ReRobApp, a modular and open source software framework for robotic rehabilitation and human-robot interaction. The authors are researchers from the Robotic Rehabilitation Laboratory of the University of São Paulo. The proposed schedule will give a brief introduction, the problems are exposed, followed by the justification, architecture of the framework, development of an application, serious gains, the experimental setup, results obtained, and finally the conclusions. Physical therapy combined with mechanical, robotic, electrical, and multimedia systems represents a promising field for the development of rehabilitation tasks, opening up possibilities to new branches and rehabilitation assisted by robots. Problems. Working with robotic devices involves the inclusion of different sensors and actuators, which can present different communication protocols, which makes it vitally important for the researcher to know in detail the operation of each of them, leading to delays in some of the tasks. The second problem is delays due to communications, which can be caused by inexperience using inadequate and inefficient programming. Finally, emphasizing the previous knowledge of various available technologies and tools and apps, leading to confusion and stress of the part of developers. A problem of delays or misinterpretation of data from a sensor can lead to undesirable behavior in robotic devices. Justification. The justification for carrying out this project is to improve the skills of researchers by automating tasks that are generally difficult and non-trivial, especially in the area of robotic rehabilitation. Framework. The proposed framework has the following architecture, with three main bases, the first of which is communication, which works as a bridge between peripherals and programming logic. Specifically, it has CAN communication. TCP and UDP servers are clients and sockets are serial. Some of the devices that are compatible with these protocols are the robots that our laboratory has, motor controllers such as EPOS from Maxon Motors and ESP32. Another of the bases of our framework was the inclusion of the Armadillo library for mathematical and linear algebra purposes. In a more recent version, AHEM was added. These libraries allow for storage arrays and vectors in text files, which can be processed offline using MATLAB and or Python. Finally, a graphic framework was integrated, EMGUI, that is easy to implement and is useful for creating buttons, graphics, text boxes, and more. It is executed on SDL, which allows working with textures, making it possible to develop games. Proposal. Based on the developed framework, a desktop application will be created where components such as rehabilitation robots, electromyographic sensors, functional electrical stimulation, and serious games will be included. Finally, implement a calibration protocol for the FES, additional open mesh control with FES, along with two game modes, and take samples with some experiments. ReRobApp. The developed application looks like this, developed entirely in C++ and use block programming. Some of the created blocks have different behaviors because the mathematical operations don't consume high times for their execution. They must also be processed sequentially. Synchronous behavior was chosen, unlike the blocks that function as an interface with other applications or devices. Since a request to these blocks may take longer than expected and may cause failures, their operation is asynchronous. In addition to the electrical stimulation block, it has a calibration sequence that sends a signal to the form of a ramp to quickly find the optimum stimulation current and frequency for each individual. Serious games. Two serious games were developed. The first allows the interaction of a single player, where he has to follow the desired path, and the second allows a competitive game mode between two players. The movements of the game elements are restricted to a single degree of freedom, with movements in the vertical axis. Open-loop phase impedance control. Two robots with an electrical actuation nature were used, but with different mechanical systems. One of them used a linear actuator and the other a series elastic actuator. Therefore, the torque controller block is added. The operation is basic. In the UFO game, when the desired trajectory is positive, the phase will be activated, facilitating the dorsiflexion movement. And in the competitive game, when the speed of the subject is positive, the phase will act for a short instant of time to assist the movement of this in the same way. Experimental setup. The proposed setup has the following structure, where electromyographic sensors are used to capture the muscular activation of the subjects, a functional electrical stimulator to assist in the movements. The games show on a screen near each subject, and the two robotic devices dressed in each individual. Finally, everything is managed by the proposed application. These experiments were approved by the Ethics Committee of the University of São Paulo. The first test has repetitive motions in which the stiffness and damping constants of the robots vary with each repetition. The current values and pulse width of the subjects were the result of the previous calibration. The second test involving the two subjects is a competitive task, where the difficulty of the movement varies linearly with their scores in the game. Once the equipment is installed and dressed, each subject has this following appearance. Results. A small video of a subject participating in experiment 1 is shown below. The subject is trying to follow the trajectory with ankle movements. Phase is activated when lining is visible. This article doesn't go into detail about the data obtained, but expected behaviors can be seen, such as a change in movement speed when the phase is activated, as it is in this case. In this clip, you can see two users in competitive play, each using a different robot. The movements made by each of the subjects are shown in the following graph, where the blue and red boxes represent the state of the phase, and the curves the angular velocity of the ankle. In the central table, you can see the movements where the difficulty of the game was altered due to the change in the score. Conclusions. This framework allows the creation of complex rehabilitation scenarios through simple blocks programming logic. We demonstrate the robustness and scalability of our framework through two case studies that include the same time. Two robots for ankle rehabilitation, phase actuators, EMG sensors, and serious games. Our efforts with ReRobApp aim at fostering an intuitive development environment to facilitate both engineer and therapist work. The framework allows the possibility of adding more components and creating more holistic and engaging rehabilitation environments, aiming at protocols that involve at the same time a greater number of subjects. The necessary documentation and source code is available on my GitHub. Thanks for your attention.